Next, we have Dankrad Feist, who is working at the Ethereum Foundation, ETH 2.0, and he's going to talk about validity and the future of blockchains, and assume mostly Ethereum.
So yeah, I wanted to talk about validity and the future of blockchains. So this is about the trying to do a classification of the different approaches to execution that have been suggested recently in the context of sharding, and look at what their advantages and disadvantages are. So as an outline, I will start with giving like a short recap on like how sharding works in terms of like committees, which is like one approach to scaling and making sure that things are valid and available, and then data availability checks. I'll come to the different execution models that we're currently discussing, which is kind of like one which I call the classic execution model, which is basically like what we're doing now, a stateless execution model, and rollups. And then I will evaluate these on different dimensions which I think are relevant, and then which we should consider. Okay, so blockchain scaling. So two approaches that can be used together or separately are committees and data availability. So in traditional blockchains, we have this property that consensus nodes always attest to two things. One, which traditionally has been considered as trivial, but more recently we know that it's not quite so, is like that the data is available, that the transactions included in the block can actually be found by any participant who is willing to or trying to download them. And the second part is that a state transition is correct. So in some cases, this might be very trivial, like on Bitcoin, just that only valid UTXOs are spent. More commonly, for example, for smart contract chains, that will be a post-state route that is supposed to be correct. In sharded chains, we get these same guarantees, or we try to get them using the committee design. So the way that happens is we have a beacon chain and a shard chain. And the idea is that the beacon chain will generate a random committee. And this committee will have a look at the shard chain, look what is the current block, check that it's both valid and the data is available, and then come back to the beacon chain and sign an attestation saying that this is the case. And because of the property that this committee is completely randomly selected, we basically have tried to get a guarantee that it's some property still holds on, like that the majority is honest. So for example, like if 2/3 of the beacon chain validators are honest, then we can, by making the committee large enough, we can get a guarantee that at least half of the validators in the committee will be honest. Now, a kind of orthogonal approach is to ensure data availability via erasure coding. So the idea behind erasure coding is this: we have like some original blocks of data. So for example, here it's D0 to D4, and we extend it using a Reed-Solomon code, which basically means we extend it as a polynomial that's completely determined by the data on the left. And so, for example, if we choose the coding rate 0.5, that would mean that if 50% of the blocks are available, then this guarantees that the whole data, we can reconstruct the whole data from the available blocks. And this can be used as follows. If we erasure code all the blocks, then a consensus node can sample some random of these chunks, like in this case. And if the sampling concludes that 50% are available, which can be done by downloading much less than 50% of the data if you do random sampling, then you get a guarantee that you can download the whole of the data without actually downloading all of it. So this is a scaling mechanism that allows us to know that data is available without downloading it all. This kind of allows a different kind of design, sharded, or not necessarily sharded, but could be sharded design. That's, yeah, for example, suggested by Lazy Ledger, where instead of having a committee, you just need to include a data root of a shard chain block. And that in itself is enough of a guarantee, if you do the data availability sampling, that data is available. Now, if so what this cannot guarantee, however, is that any sort of guarantees on what's in the data. So like if we do this, then we will not be able to promise that there's a valid state transition in the data or anything. It could just be complete garbage. And another, so this is kind of a caveat of this design. One of the problems that we don't know yet whether this is a problem or not, but currently nobody has really shown that this can be done with very low latency. So even if we want a chain that only guarantees data availability and no state transition correctness or validity, there is the question whether this can be done in a few seconds, as like, for example, a committee can work with like maybe 5 to 10 second latency, whereas in this case, this is not clear yet whether like both distributing the sample chunks in a peer-to-peer network and doing the sampling can be done on that sort of latency scale. But if that can be done, then this is like a very promising and elegant design that gets like rid of a lot of the complexity of sharding. So now let's talk about some execution model. Well, we have of course, the classic model, which is basically just a block with transactions and a post-state root. But like I'm only like mentioning the sort of advances on this here. So like one of the things that that has been proposed is to transition to a completely stateless execution model. What this means is that any block doesn't come just with the transactions, but actually with all the state that these transactions access and complete witnesses for all these accesses. What it means that for consensus nodes, it's now possible to verify the validity of the block without having any of the state that this block is operating on. So in terms of like in sharded blockchains, it's kind of very clear why this will be a huge advantage, because before we have this problem, we send a committee to a sharded blockchain, well, but now it needs to somehow download all the state in order to verify blocks. And that could be many gigabytes. So we can't really randomize committees very quickly. Well, if we have stateless execution, then we can, because there's no prerequisite to download any data. So we, like any validator hopping on a shard, can instantly start validating it. But also, even like without sharding, there's actually a big advantage to the stateless model, because it means that like one of the big bottlenecks in execution is actually typically accessing the state. So both like accessing RAM, if you want to keep the whole state in RAM, or accessing any external storage is like a huge, like comes with a huge latency. That's very expensive. Now the rollup model is basically, we don't care about, like the consensus doesn't actually care about the validity of the content of the block at all. Basically, like the block is just treated as like a big blob of data, and the consensus nodes only come to consensus on that the data, like on the sequence of the data and that it's available, but not on any sort of a post statehood or anything. So that's completely like in someone else's hands. And there are basically two flavors of this rollup model. One is optimistic rollups, which is basically that that you just trust that everything is correct, but there's a fraud-proof mechanism that that will ensure that if anything incorrect gets included, then anyone can submit a fraud proof, and that error basically gets rectified. And the other flavor is so-called ZK rollups, and they use computation integrity proofs, like often called zero knowledge proofs, but in this case, we don't actually need that they are zero knowledge. We just need them to vouch for computational integrity. And they basically prove that the whole execution was done correctly and a state root was computed correctly from this. Yeah, I mean, there are also rollups in that, like the consensus nodes now would only have to verify this proof, and that's typically a very easy and quick operation. Okay, now let's look at these from our different dimensions. So the first one I want to look at is what consensus nodes have to do. So consensus nodes, basically in the classic model, they have to do like full computation. They have to like compute the full state transition. They have to keep the state and everything. There's a stateless one, which is kind of in between, like where some of the load is taken off the consensus nodes. They don't have to maintain the state anymore, and they don't have to access the state anymore. So even if they do maintain the state, actually, it becomes more efficient because they don't necessarily have to access all the state to verify transactions. And then on the right, we have the rollup, where like the consensus nodes don't have to compute anything anymore. They just have to verify data availability. And I drew this dashed line where there's like a transition from where you do need some sort of committees to do sharding and where committees are no longer needed. If you are in the rollup land on the right. Now, the second thing that is interesting is the so-called sequencer, or what I call sequencer complexity. So the sequencer is the one who will prepare blocks when normal consensus nodes. So in classical like blockchains, it's basically the people who produce blocks and who maintain the consensus are the same. But in some of these constructions, we need different kinds of nodes that actually have the ability to contribute blocks and construct them. And I call those sequencers. And so on the very left, in terms of we have the classic and the optimistic rollup constructions, where basically the sequencer is the same as a normal node and there's no extra complexity. Then in the middle, we have the stateless construction where a sequencer will need to do some more operations than a normal consensus node. So in this case, they have to maintain the state and they have to maintain the witnesses, where the latter one is typically dominant. And then if we do the ZK rollup construction, where we have full computational integrity proofs for all state transitions, then we have like a very high requirement for sequencers, which is probably at the moment even like way too high to be in any way realistic. So that's still in the future. And then the third interesting dimension is the finality guarantees. So basically, in some cases, so for classic execution, stateless and ZK rollup, the finality of computation is the same as consensus. So like once the consensus is final, like we know that our transaction has been executed, for example, that we received some money or some other assets, and we can finish the transaction in the real world. Whereas in the case of the optimistic rollup, obviously, like we might have to wait for whether a fraud proof is coming in that might revert transactions, that might even revert not just like our own transaction, but some transaction that it was based on. So basically, we don't get this instant finality. That's the same as when the consensus reaches finality. Okay, so why are these dimensions so relevant? We care about how much load a consensus node needs to take, because we need 2/3 of the consensus nodes to be honest. And if the requirements for running a consensus node is high, then that means that it's easier for centralized actors to take over the network. So that's why we try to keep the requirements for this as low as possible, so that basically like it's possible for like average people to run a node in their basement, and it's not just like something that is exclusively available to, let's say, like large and powerful institutions, where the state could quite easily, or states could quite easily attack them and enforce censorship, for example. Now the sequencer complexity is also relevant for censorship resistance, because obviously if you can overtake all the sequences, then you can still censor transactions. But it's a bit different, because in this case we only need one single honest sequencer to maintain the censorship resistance. As long as there's one, like you can just give your transaction that someone's trying to censor to them, and you can still get it included. So there's a bit of a difference between the consensus nodes and the sequencer, in that for one, in order to enact censorship, you need to overtake a large number, you need to keep a large number of nodes. Sorry, let me repeat that. So you need a large number of honest nodes to maintain censorship resistance, whereas for sequencer complexity, you just need one honest sequencer. So here the aim would be, like my personal sort of feeling is that ideally we want to find something where it's easily possible that we have like 100 or so independent sequencer nodes in the world, and so that would make it very difficult for any actor to enforce censorship among them. And then the final thing is the finality guarantees. So as a user, I want that my transaction is very quickly finalized, that I can trust that everything has been correctly executed, and I can, I don't know, whatever, drive away with the car I just bought. And so the problem is, if we have poor finality guarantees, that means you need extra effort on the user side. So either you have a long waiting time to wait for the fraud proof to come in. Well, that's pretty bad. Or the alternative is, for the rollup case, for example, people will say, well, yeah, like you just validate the whole rollup yourself, and then you know there won't be a fraud proof. Yeah, but I mean, then the users suddenly have to run the expensive nodes to maintain the whole rollup. So that's not a good trade-off either. So that's why we care about finality guarantees. They basically ensure that we have good UX. Okay, and this is basically my summary from these different for these different execution models. So the numbers on the estimated throughput are like very rough estimates. Well, except for rollups, we can roughly say it, like how they perform on the current Ethereum main chain. So we expect them to be about 200 times faster. It's still a big and very interesting question how much acceleration stateless execution itself already provides. Then so this 3 to 5 times is like a very rough estimate we have at the moment from the TurboGas team. And yeah, as we see, like unfortunately there's currently no no perfect solution in the space. Like all of them have very significant disadvantages. The big one is, yeah, I mean, ZK rollups may sound like the ideal long-term solution. However, we do not know yet at what point doing proofs for full state transitions becomes realistic. I would estimate at somewhere in the range of 3 to 10 years. But even if it does, we still have the question, like, how much will a sequencer that can provide this proof cost? Like, if that's in the range of $10 million for one sequencer, then that's still a pretty big question mark whether this can really provide a censorship-resistant way forward. Yeah, from my estimate, it's basically very possible that we have, I wouldn't call it a trilemma, it's more a practical trilemma in the sense that it is solvable if, like, we had extremely fast zero-knowledge proofs, but until then, we might only be able to choose between two of high scalability, finality, and censorship resistance. Okay, thank you very much. Are there any questions?
Thank you, Dankrad. That's a really interesting talk on all the possible scaling solutions. I wanted to ask you if you can elaborate a bit more on what exactly is the stateless execution, because for me it sounded like very close to the, like, do the clients have to prove what they are transacting, or they just show the state directly to the validator and somehow prove that that was a correct state?
Right. So it's basically based on the idea that you always commit. I mean, most smart contract chains will do that anyway. You commit to your state always, like you commit to the state of all the accounts in every block. Mm-hmm. So the stateless execution, basically you can see each transaction will only typically access a finite subset of that state. And so basically what it does is you include, in your transaction, you include that state as well as witnesses that prove from the commitment. So basically the Merkle witnesses, if you use Merkle roots, to prove that the state was, like, accessed correctly, like, yeah. So basically, I would say, in a way, you could say it's like one part of the zero knowledge proof, if you want, but it only proves all the state accesses, not the virtual machine itself.
Okay, so basically, you provide the trace of the execution and show that, like, everything you access is correct.
You don't necessarily have to provide a trace of the execution, because, like, the node, when it executes the virtual machine itself, it will notice, okay, it wants to access this part of the state, and you have provided, like, then presuming you have provided that, it will just take that, and you have provided proof that it's correct, and just use that.
But
you haven't provided it.
Right, yeah. You need to pre-execute everything so that you can give all the commitments and all the witnesses.
Yeah,
that's what I mean. And then they just check that whatever you provided is consistent and execute. Okay, makes sense. Cool. So thank you very much, Dankrad.